Hello folks, in this video clip today I'm gonna go over rational functions and some of its basic properties. Okay, so let's start with the definition. A rational function is a function that looks like this. F of x function is a fraction where the numerator is a polynomial and the denominator is also another polynomial. So in short, a rational function is a function of the form a polynomial divided by another polynomial. Okay, so whenever you guys see a function that looks like this, because a rational function. Okay, let's box this. And let me give you some example of rational function. Example. Say f of x is equal to 2x minus 1 over 3x squared plus x plus 2. This is a rational function where numerator is a polynomial of degree 1 with leading coefficient 2. Denominator is a polynomial of degree 2 with leading coefficient 3. Okay? So from now on in this clip today, I'm going to denote this rational function by p of x over q of x, where p of x represents the polynomial on the numerator and q of x is representing the polynomial on the denominator. So I don't have to say the whole name again. Just p means numerator and q means denominator. Okay? And like our regular fraction, we have two kinds of fraction: proper fraction and improper. Proper means the numerator is smaller than the denominator. So in terms of polynomial, we are talking about the degrees. In this example right here, this is degree 1 over degree 2. It is a proper fraction. Okay? Otherwise, be improper. So say this one, f of x equal to 2x plus 5 over 4x minus 1. This is degree 1 over degree 1. This is an improper fraction. Okay? Let's recall this type of function. F of x equals, say, 5 over 2x minus 1. And I claim that this one is also a rational function. Why? Because the numerator right here is actually a polynomial. If you take a look at the clip about the polynomial function, number 5 constant is a polynomial of degree 0. And the bottom right here, the denominator is a polynomial of degree 1. So proper fraction, this is a rational function. Okay? So obviously this one is also, by our definition, this is 5 over 2. Rational function, polynomial of degree 0 over polynomial of degree 0. It is a rational function. Okay? So this one, f of x equal to 3x squared minus 2x plus 1. Looks like what? It looks like a polynomial, right? But I claim you can also think of it as a rational function if you write it this way. So it is a rational function. Another word, all polynomial functions are actually rational functions, but not the other way around. Okay? Let's move on to some basic properties of rational functions after we got definition. Some basic properties. First of all, I'm going to talk about the domain. What domain of rational function is kind of significant in here because we're dealing with a fraction. Okay? So let's start with an example then. Example. Take a look at this fraction. F of x equal to 2x minus 1 over x plus 2. Recall what it means by domain. Domain is the set of all valid input x, so that when you plug x in, you can have an output. So looking at this function right here, I claim the domain of this function is all real numbers, except x equal to -2. Why not -2? It is because -2 is a 0 of this denominator right here. When you plug in -2 in for x, -2 plus 2 equal to 0. And by what we learned before, if you have denominator equal to 0, something divided by 0, the fraction is undefined. Okay, so domain is all real numbers except -2. Okay, so in short, we can use set notation to represent it. All real number x, and x cannot be equal to -2. Or you can use the interval notation to represent the domain. Any numbers from -infinity all the way to -2, not include -2, and then union -2 to infinity. You don't have to write all three when you get to your homework, quiz, or exam. Just one of those three ways of writing the domain is good. Okay. Another example. How about this f of x equal to 3 over x squared minus 4x plus 3. Find the domain of that thing. Okay? So, the first thing that you should do is try to factor out the denominator. So you can find all the linear factors of it. And I have this. This is f of x equal to 3 is on the numerator. We're not going to touch it. Denominator is x minus 1 times x minus 3. This is, you factor this out. I give you very straightforward and simple numbers in here. -4 is -3 times -1. And -3 times -1 is +3. So you have this. And the domain is what? All real numbers. So let me use a set notation right here. Okay? X cannot be equal to 1 and x cannot be equal to 3. Curly bracket. Okay? Or you can use the interval notation. -infinity to 1, union from 1 to 3, and then union from 3 to infinity. Set of all real numbers except for 2 values, 1 and 3. Okay? When we talk about very first thing, the domain of a rational function. Next property, we talk about the graph of rational function. There is a very special thing about the graph of the rational function called the asymptotes. Asymptote is a straight line in our definition, where the graph of the rational function is going to get closer and closer to the asymptote, to the line, but never intersect at infinity. So we're going to talk about 3 types of asymptotes today. First, we will talk about the vertical asymptote, and then the horizontal asymptote, and then the third one will be the oblique asymptote, which is the diagonal line. All right, so let's start with the asymptote. So probably number 1 was the domains. How about number 2, vertical asymptote? Okay, let's abbreviate it by VA, vertical asymptote. Okay, so let me start with another example. How about this? F of x is equal to 3 over x plus 2. Make it simple. Start over. The domain is what? All real number x, and then cannot be -2. Okay. And I claim that finding the vertical asymptote somehow related to finding the domain of the rational function. And I claim that the vertical asymptote is x equal to -2. Okay? We're going to talk about this in more detail when you guys move on to calculus 1, when we have something called the limit of the function, and we can take the limit and we can talk more. For now, let's just compare between the domain and the vertical asymptote. Domain is what? All real number of x cannot be equal to -2. Vertical asymptote is x equal to -2. And let me sketch the graph of that thing. X-axis, y-axis right here. vertical asymptote of x equal to -2. This is the line x equal to -2. Okay? And the graph, let's use green color. The graph going to look like this. And like this. As you see, that the two green curves are approaching the vertical dotted red line, but never intersect at infinity when x getting closer to either from the right or from the left, and the function tends to go either positive infinity or negative infinity, but never hit the vertical line. Okay, so we have the vertical asymptote, and obviously in this example you see that the graph actually have another type of asymptote. Look at the x-axis right here. The graph is also getting closer and closer to the x-axis, with x either go to positive infinity or x approaching negative infinity. The graph is getting closer to the horizontal line. So the second item will be covered today is horizontal asymptote. Let's save it for later. Okay, I'm going to come back to the vertical asymptote. Let me give you another example. How about this? F of x is equal to 2x minus 1 over x squared minus 4x plus 3. We're going to go over the whole thing. So first of all, let me factor out the denominator. 2x minus 1 over x minus 1, x minus 3. And the domain is all real number x. X cannot be equal to 1. X cannot be equal to 3. We talked about this already. Okay? Now let's talk about the vertical asymptote. This graph diagram is going to have two vertical asymptotes, and they are x equal to 1. The second one is x equal to 3. Alright? Let's sketch the graph of this one. And you're going to see. I'll make sure that I got it right. Let me start with graphing my calculator first. Y equal to 2x minus 1, then over x squared minus 4x, and then plus 3. Okay, the graph. Alright, I see it here. See the whole thing. All right, I see the graph. Show it to you. This is the x-axis. This is the y-axis. I use red color for the two vertical asymptotes. I got two of those. This is x equal to 1. Another one right here. X equal to 3 right there. And the graph looks like this. Okay. Let's use green color for the graph. Make sure that I copy it right. Graph looks like this. Oop. Never hit the asymptote, okay? Okay. This right here. And you see what? The three pieces of the graph are actually approaching the vertical lines x equal to 1 and x equal to 3 right here. One from the left, one to the right, and the middle pieces approaching both vertical asymptote from both sides. And of course, in this graph, you can clearly see that we have another asymptote, which is the horizontal one right here. The left piece of the graph is approaching the asymptote from the left, from under, and the other one right here approaches the horizontal asymptote when x goes to infinity. Okay, and you have two vertical asymptotes in this example. Okay, We have two examples. Hopefully you guys see the connection between the domain and the vertical asymptote. However, we have some exceptions, so take a look. We go to the third example. What my problem is this: f of x equal to 2x minus 6 over x squared minus 4x plus 3. And we're gonna go over the entire problem like before. This is 2x minus 6 over x squared. Oh, a factor this out, so it's gonna be x minus 1, x minus 3. All right? And the domain is gonna be very similar to the examples that we learned before. All real number x. X cannot be equal to 1, x cannot be equal to 3. What about the vertical asymptote? As you may expect that we have two vertical asymptotes, should be x equal to 1 and x equal to 3. However, in this example, I claim that you will only have one vertical asymptote. And you guys are going to see why. In here, what if you factor out the numerator as well? 2x minus 6, factor out of 2, you got 2 times x minus 3 in here. You see something special about this example? We have a common factor between the numerator and denominator, which is x minus 3. It's going to be canceled out for the vertical asymptote. Domain stays the same, okay? We don't cancel out for domain. So actually in here, you only have one vertical asymptote, which is x minus 1. All right, so in general, you want to find the vertical asymptote. You guys are going to follow a couple of steps. First of all, try to factor out the denominator into all linear factors. And make sure that you cancel out all the common factors between the numerator and denominator. Whatever linear factor left over in the denominator, going to give you, the zero of those is going to give you the vertical asymptote. All right? And that will be taking care of all the vertical asymptotes, possible vertical asymptotes that you may find in the rational function. One more time, rational function, factor out both numerator and denominator. Cancel out every single common factor that you see. Okay? Whatever left over in the denominator is going to give you vertical asymptote. Okay? That was vertical. Next, let me move on to horizontal asymptote. Number 3, horizontal asymptote. Abbreviated by HA. Okay. The key to look for the horizontal asymptote is to compare the degree of the numerator to the degree of the denominator. So I'll say it this way. Compare the degree of P of x to the degree of Q of x. First of all, DEG stands for degree, okay? And as I mentioned in our definition in this video clip today, I denote P of x for the numerator of the point of the rational function and Q of x for the denominator of the rational function. So just compare the degree and you have a hint about the horizontal asymptote. And again, since this is pre-calculus algebra class, we haven't talked about limit yet. So this is pretty naive way to talk about horizontal asymptote or asymptote in general. But I claim later on, when you guys move on to calculus and we have more tools in hand, then we're gonna talk about those things in a more professional way. I'm not saying that this, what I'm telling you is wrong. It just learn it by observation first, and then we get into the technical algebra for the next course. Okay. So let's start with the first type. So let's talk about how about A then. If the degree of the top is smaller than the degree of the bottom. Okay, so you know this fraction is gonna be a proper fraction. Then you will always have the horizontal asymptote as y equal to 0, which is the x-axis, always. Okay. as long as the fraction is proper, then you have horizontal asymptote, the x-axis. Example. We may use the same example as before. How about right here? So I don't have to write it. Take a look at the example on the right-hand side. The numerator is a polynomial of degree 1. The denominator is polynomial of degree 2. So obviously, degree of the top is 1 less than degree of the bottom, which is 2. And of course, we can find a domain. We can find the vertical asymptote. But now we can find one more thing, which is the horizontal asymptote. Example is right here. And let me find just rewrite a function here. F of x equal to 2x minus 1 over x squared minus 4x plus 3. So degree of p of x is equal to 1 less than degree of q of x, which is equal to 2. So the horizontal asymptote is y equal to 0, which is the x-axis. And I have the graph right here already. Okay. X-axis right here, origin. Origin's right here. Y-axis right here. X-axis right here. And the graph, the green curve is approaching the x-axis, but never intersect. Okay. Doesn't matter how much smaller or how much smaller the denominator compared to the numerator. How much smaller the numerator compared to the denominator. Doesn't matter. Say degree 1 out of degree 3 or degree 1 out of degree 1000. As long as you have degree of the numerator smaller than the degree of the denominator, then for sure you're going to have a horizontal asymptote. Okay, at y equals 0, which is the x-axis. Okay. Second case. What if they have the same degree? So I'm going to give you the second case. B right here. Degree of the numerator is the same as degree of denominator. Example. We'll talk about the formula first. The horizontal asymptote will be y equal to a fraction of the leading coefficient of p of x over the leading coefficient of q of x. In other words, you're going to find the horizontal asymptote by making a ratio of leading coefficient over leading coefficient. Okay? Example. How about this? F of x, example, equal to 6x plus 1 over 2x minus 8. Okay, so this is a good chance to start the problem over. So let's talk about the domain. To find a domain, factor out denominator. 6x plus 1 over 2 times x minus 4. So you see the domain is all real number x. X cannot be equal to 4. Okay? And as you know, x minus 4 factor on the top, so there will be no cancel out. Alright? And talk about the vertical asymptote will be x equal to 4. Okay? And horizontal asymptote, the top is polynomial of degree 1. The bottom is also polynomial of degree 1. According to what I showed you right here, the horizontal asymptote will be y equal to 6 over 2, which is equal to 3. Alright? And now let's talk about the graph function. Let me sketch the graph roughly. And this is my y-axis. This is the x-axis right here. Y-axis. So the x-axis a little bit lower. Right here. Okay. So the vertical asymptote is x equal to 4. Right here. Horizontal asymptote is y equal to 3. Right here. This is x equal to 4. This this line right here is y equal to 3, and this is the origin. Okay, and the graph gonna be like this. Let's say, what color do I use? Green color. Okay, graph gonna be like this. There are two curves, two green curves, two pieces for the graph. One is on the right hand side of the line x equal to 4, another one is on the left hand side of the vertical line x equal to 4. And then when x goes to infinity, past infinity, the graph is approaching the line y equal to 3 from above, but never never touches. And when x goes to negative infinity, the graph is getting closer to the line y equal to 3 from below, but again, never intersect, never touch. Okay? The third case is the degree of the top is bigger than the degree of the bottom. C. Degree of P of x is greater than the degree of Q of x. And what happened? Then we have no horizontal asymptote. Okay? So if you look at the rational function and you see the degree of the numerator is greater than the degree of the denominator, you know for sure that the graph of that function will not give you any horizontal asymptote at all. Okay? Right. Number 4. Let's talk about the oblique asymptote. Oblique asymptote. Denoted by OA. This is the asymptote that has a slope, okay, a positive slope, make a diagonal line. And you can only have the oblique asymptote only if the degree of the numerator is exactly 1 more than the degree of the denominator. Say degree 5 out of the degree 4, degree 4 out of degree 3, degree 2 out of degree 1, and you have the oblique asymptote. So degree of P of x equal to degree of Q of x plus 1. Okay? The bottom plus 1 equals to the top. You will have the oblique asymptote. And how to find the oblique asymptote? You're going to find the quotient of long division. Okay? Okay, so let me give you an example. F of x is equal to 3x squared minus 2x plus 1 over x plus 2. Obviously, this is a rational function. The top is a polynomial of degree 2 with leading coefficient 3. The bottom is a polynomial of degree 1 with leading coefficient 1. So let's start from over. Domain or real number x. X cannot be equal to negative 2. Okay? And the vertical asymptote will be x equal to negative 2, because when I plug a negative 2 in here, the top will be a positive number, so it's never cancel out. So the top doesn't have a 0 of x equal to negative 2, vertical asymptote. So there's no factor to cancel out. Okay? Horizontal asymptote? None. Degree of the top is bigger than the degree of the bottom. No horizontal. What about oblique? To find the oblique asymptote, first of all, we have to check for the condition. Degree 2 out of degree 1. Is that good? Yeah. 2 is exactly 1 unit bigger than 1. So we do have an oblique. To find the oblique asymptote, y equal to something, we have to do long division. And this